Hi everybody, this is Dr. Prafulla Dikshit and I'm back with yet another video on time series analysis. Herein we're discussing the very basic concepts of time series analysis, which are the foundation stones of the analysis of time series, so to say, the concepts like correlation, regression, and many other concepts, right? Which form the building blocks of the thinking that goes into the analysis of time series. Now, in the last video, if you might remember, we arrived at the basis of the transformation of the concept of correlation to autocorrelation as it applies to time series. And we said in the last video towards the end that in the next video or the subsequent videos, we'll discuss or we'll arrive at, so to say, a mathematical formula, statistically applicable mathematical formula of autocorrelation, and from there on, we'll discuss how to do autoregression on time series data. So let's go back a little bit to the climax of the last video. So in the last video, if you remember, we got the basis for the conceptual transformation of correlation to autocorrelation. Now in this video, we'll see how. So we learned it through a comparison between two correlation concepts, and this is how it looked. We had correlation versus autocorrelation. So we got to know that correlation is the ratio of the covariance to the variance of the two variables, say x and y, versus autocorrelation is the ratio of the autocovariance to the autovariance of two variables, say xt and xt plus t. Now herein there is a slight amendment, right? Now this amendment is required now that we are going to discuss the mathematical concept or the mathematical formula of correlation and autocorrelation, because we are looking at it in a more a detailed and more precise way. So we discussed it at a conceptual level, but if we have to derive a mathematical formula, we have to be more and more specific. So we insert or introduce a new term called square root of. Okay, and I'll just explain in a bit as to what it means here, right? Okay, so right, okay, and the same thing goes for autocorrelation. So the square root of the autovariance. Now, as you can see, first of all, that the square root of the variance of the two variables, say x and y, means that we are talking about the standard deviation, first of all. So in mathematical terms, both standard deviation and variance are identical concepts. Variance is the square of the standard deviation, or in other words, standard deviation is the square root of variance. However, when we are deriving a mathematical formula, we have to be specific. So we introduce square root of the variance of the two variables, say x and y. And similarly, we talk about the square root of the autovariance of the two variables. Now, as you might see, I have placed a cut on this auto part, autovariance. That's because auto right here is kind of redundant, because we are talking about two variables, right? So this is just to explain, auto is just to explain that we are in fact talking about a single variable, but with a lag of k, right? So it's actually, in fact, it's if we talk about the time series, it's a same mother time series, which is a variable in itself. But herein from that mother time series we derive two sub time series, which is xt, and its lagged time series, which is xt plus k. Right. So since they are from the same series, that's why in order to denote this redundance of you know the mentioning the term auto, I've placed a cut on this word. So if you might remember, these are the slight amendments from the previous video. Okay, so two important points. One is that although correlation is the ratio of the covariance to the variance of the variables, but variance herein, when we talk about variance mathematically, is precisely measured in terms of the product of the square root, not exactly the variance of the variables, right? And this is the same for autocorrelation as well, right? Now this was based on the following observation, which is okay, and this expression, that is the correlation of xt and xt plus k, implies in itself an autocorrelation of xt with its lagged values, right? So that's why we denote it as xt comma k. So correlation of xt comma xt plus k implies an autocorrelation of xt comma k, right? And we can name this equation as 1. Okay. So we also saw how in notational terms the correlation of xt comma xt plus k, okay, right here, the same expression which is here, is equal to the covariance of xt comma xt plus k divided by the standard deviation. Okay, it's not variance but the standard deviation. Okay, so this is consistent with this amendment that we made right here. Okay, so it's the correlation of xt and xt plus k is equal to the covariance of xt and xt plus k divided by the standard deviation of xt and standard deviation of xt plus k, right? As in, it's a ratio of the covariance of the two variables to the product of the standard deviations of the two variables, which is a way of putting the value of the variance itself. It's an indirect way of measuring the variance of the two variables, right? Xt and xt plus k. Okay. And this expression right here, we've named it as 2. So we have two equations, 1 and 2 right here. So now based on 1 and 2, we can say the autocorrelation of xt comma k is equal to the covariance of xt comma xt plus k divided by the standard deviation of xt multiplied by the standard deviation of xt plus k. And this expression right here, we name it as 3. Okay, so you can see a pattern here, right? So we have correlation of xt and xt plus k implying autocorrelation of xt and xt plus xt comma k, which is 1, and the correlation itself is equal to this, and that is why from here, from 1 and 2, we derive this expression, that is the autocorrelation. So we have autocorrelation of xt comma k equal to the ratio of the covariance to the product of the standard deviations of the two variables. It's kind of intuitive that since standard deviation is a square root, that it requires two measures of standard deviations multiplied to get a variance, right? So square root of variance is equal to the standard deviation, and square of standard deviation is equal to the variance. So if we can say that standard deviation of this into the standard deviation of this would kind of give us the variance if these two values would be close enough, right? And we'll see how. We can also put it slightly differently, and we can say that, and also as we've seen from the previous video, that graphically and intuitively, Autocorrelation is the ratio of the autocovariance to the square root of the autovariance of the two variables, say xt and xt plus k. However, on a closer look, autocorrelation is the ratio of the autocovariance to the autovariance or the square root of the autovariance of xt itself with a lag k. And we can express this as this expression, this equation right here, autocorrelation. K is equal to covariance of xt comma xt plus k divided by the variance of xt comma k. Okay, and we can express this, we can name this as 4. Okay, this is equation 4, right? Therefore, substituting 4, this expression 4, this equation 4 into equation 3, we can very easily infer a very important observation, that is, the variance of xt comma k is equal to the standard deviation of xt multiplied by the standard deviation of xt plus k. Now this is the same expression or same relationship that we had just talked about a few moments ago. At that time we talked about it intuitively, but right here we have some kind of a conceptual, to some extent a mathematical, an evidence or a proof of this. That is, the variance is the square of the standard deviations of a variable. Under what circumstances would these two expressions equal this? Okay, and we can say logically that this would happen only under this circumstance, at least approximately, wherein these two values are approximately, or these two variables are approximately close to each other, right? Now, as we saw, this condition can hold true for values wherein these two expressions are close together, and this is possible only where k has a small value. So k, for example, has a small value like 1, for example, right? So for lag k equal to 1, we can have xt comma k where k equal to 1, and xt looks something like this, wherein xt is equal to xt comma xt plus 1 comma xt plus 2 comma xt plus 3 and so on and so forth, wherein there is a single lag at every successive value of x. This k equal to 1, which is a very small value of k, is an example of a necessary condition for equating the expressions in 3 and that in 4, right? Because everything else being same, the variance has to be equal to the product of the standard deviations. And since variance is the square of standard deviations, the product of two standard deviations can be equal to the variance of some single expression, something like xt comma k, only when xt and xt plus k are very close together, which will not exactly be the same, but will approximately be the same as the variance of the expression, right? So intuitively, we can also express this observation as this, that is, variance of xt comma k is equal to square root of, and bracket open, square of the standard deviation, okay, of xt multiplied by the square of the standard deviation of the xt plus k, okay, and or we can say, we can express it as the variance of xt comma k equal to the square root of the variance of xt multiplied by the variance of xt plus k. And this expression right here, we just name it as we name it O1, okay, right? So intuitively now we can also say that the autocovariance of xt comma k is equal to the autovariance of xt comma k, which is equal to the variance of xt plus k, uh, and which can also be expressed as the variance of xt itself. And we can, although it's not an equation exactly, but we can name this expression as, say, 5. Okay. Okay, now if we denote autocorrelation as rho, it's pronounced as rho, the equations 4 right here and this expression 5 right here uh, will actually lead us to this expression. We can say rho k is equal to the covariance of xt comma xt plus k divided by the variance of xt. This is a much more simplified way to express it, and we name it as equation 6, right? Okay. So what we have right here is forward legs, what we call forward legs. That is it is xt, and then we have xt plus k, right? So the lags are moving forward. Okay, so it's xt plus k. So, however, if we take what we call uh, backward legs, backward legs instead of the forward legs. Based on this expression 6, what we get is this expression, right? Uh, we can contrast this with this. It's simply a backward leg expression of this equation right here. So we have rho k equal to covariance of xt minus k comma xt divided by the variance of xt. Okay, now this is just that in this case we are going forward in time, and in this case we are going backward in time, and this expression right here we can name it as 7. Okay, now herein rho k is the autocorrelation of xt at lag k, and covariance of xt and xt minus k is the covariance of xt minus k as expressed here. Okay, so far we've come a long way and discussed the value and understood the value of autocorrelation, right, in an intuitive way. But more importantly, we've arrived at and we've covered almost more than half the distance, close to almost 80 to 90% of the journey towards arriving at a mathematical formula of autocorrelation. Okay. So in the next video, we'll first of all we'll provide a mathematical and conceptual evidence for this expression right here, and also colloquially this expression, because these are one and the same thing put in two different ways, and eventually we'll arrive at this formula for autocorrelation, wherein we'll use this this evidence for this expression as a basis for arriving at the formula of autocorrelation, right? Just to give you a sneak preview of what is in store in the next video, we'll actually arrive at the mathematical formula. We'll use mathematical formula of correlation of, say, two expressions x and y, and use it as a basis to arrive at the autocorrelation. That is the correlation between these two kind of expressions, or say maybe these two expressions. Right here, xt and xt plus k, or maybe xt and xt minus k and xt, right? So this brings us to the end of this video, and if you really like this video, do give it a thumbs up. And if you think it can be useful to anybody, do share this video, and do not forget to subscribe for more such videos, and for notifications, do press the bell icon. And as always, thanks for watching. Take care. Have a good day. Bye bye.